Unit 5 Curve Sketching, Subsection 2, Applying the Derivative Tests. So there's some new curriculum bullets for this one, so let's just go through those really quick. I can check for concavity using the second derivative and use it to determine if a point is an inflection point. So those are some new words, we're going to talk about them right away. I know that vertical asymptotes exist where the function approaches positive or negative infinity from both sides, and I can find them. So we're going to talk about vertical asymptotes. We're also going to talk about horizontal asymptotes. We're going to talk about limits at infinity to figure out horizontal asymptotes and use that to help sketch a curve. And you're going to be able to determine whether a function is odd or even by the end of this subsection. So part 1, concavity and points of inflection. So remember, inflection points, we talked a little bit about them last section. Inflection points are points on a function where the function goes from increasing in slope to decreasing in slope or vice versa. At such a point, the second derivative will be 0. So f double prime of x will equal 0. Okay, awesome. We spoke last section regarding the second derivative test, and we used the second derivative test to determine if a critical point was a maximum, that's when the second derivative was negative, or a minimum, when the second derivative was positive. In this section, we're going to expand our vocabulary, and now we're going to use the term concave down to describe when a graph bends downward from left to right. So from left to right, it's going to bend downward like that. This happens when f double prime is less than 0. So this happens as we approach a maximum. So if we keep going around like that, okay, it makes a maximum. Now, of course, if we keep going, it will make a whole circle, but that's not a function anymore, and at some point we're going to turn the other way. Okay, that point where it turns, that's called an inflection point. Okay, anyways, so that one there is concave down. So again, second derivative is less than 0. Okay, then the other term is then concave up, and that's used to describe when the graph bends upward from left to right. So that is the other one, so upward from left to right. Okay, and that happens when the second derivative is bigger than 0, so as we approach a minimum. Okay, all good. So we have concave up and concave down. So this guy is concave down. We typically use CD for concave down and CU for concave up. Okay, not a big deal. Awesome. Okay, we first became aware of inflection points in Math Theory 1 when we described the zeros of a polynomial with an odd multiplicity of 3 or higher. Remember we had stuff like x plus 1 cubed? So the 0 was at x equals negative 1, and the graph kind of did a little swoopy thing like that. So that's an inflection point. Okay, on the graph to the above right, okay, that's up here again. Okay, there's an obvious inflection point at 3, 4. So that's this guy, 3, 4. Okay, so we're going from concave down, since then switching to concave up. Right, concave down, concave up. CD and CU. Okay, so the point where that changes is the inflection point. Okay, awesome. Now, there are other inflection points on this graph. They're just not as obvious to see. So this section is going to teach you how to find those inflection points and how to describe them. Okay, a couple of important things here because these are going to show up in our examples. Inflection points sometimes occur at critical points. Sometimes. Okay, remember critical points are when the first derivative equals 0. So f prime of x equals 0. They almost always occur when the second derivative equals 0. Like we're talking 99.9% of the time, but there is one of the examples that I have when it doesn't, so it's okay. And it sometimes happens when f double prime is undefined. Okay, so that's when you square root a negative or divide by 0. Sometimes they can happen there. There's also an example like that. So we have to check out all these possibilities, okay, and then we check the concavity before and after a possible inflection point. Okay, so I'm going to show you how to do that here right away. All right, so let's get on with it. So example 1, where is the curve y equals x cubed, concave up, concave down, and at a point of inflection? Okay, well the first thing we do is we figure out the derivatives. So y prime is 3x squared. Okay, and we need to figure out the critical values. So that's when the first derivative equals 0. So 0 equals 3x squared. So of course, to divide by 3 square root, anyways, x equals 0. Okay, so that is our critical value. So then we figure out well, it's y this time, but f double prime or y double prime. Okay, so that is 6x. Okay, awesome. So then we figure out so double prime is kind of what we're talking about. So we figure out, this is kind of similar to last unit, we figure out when the second derivative equals 0. So, okay, so divide by 6, and x equals 0. Okay, so 0 is our inflection point. Okay, so we already did C. Okay, now we need a point of inflection. So we have to figure out the function, so f of 0, so that's going to be 0 cubed, which is 0. Okay, so the point 0, 0 is an inflection point. Okay, awesome. Oh, sorry about that. All right, so the point 0, 0 is an inflection point, and then we're going to make a graph kind of like we did last time with the number lines. Okay, so 0, okay, that's we're doing this for the second derivative. Okay, so now we pick points kind of to the right or to the left. We can also do this algebraically by saying 6x has to be, so that's the second derivative, is greater than 0. Okay, that would make a concave up. Okay, anyways, don't worry about that. I think it's easier if we do the graph part. So we're going to pick a point to the left and to the right of 0, so -1 and +1. So when x is -1, okay, so the f double prime of -1, okay, so that's 6x, so 6 times -1 is -6, which is negative. So there's negative here, and f double prime of +1 is just +6, which is positive. So positive over here. So remember, when we're talking about the second derivative now, these are the regions of concavity. So we're concave up. Okay, concave up is this one, and that happens when we approach a minimum. That happens when the second derivative is positive. So we are concave up. Here, let's do it better. So f of x is concave up for, okay, and we're from 0 all the way up to infinity. So from 0 all the way up to infinity. And we are concave down, that's when the second derivative is negative, concave down for -infinity all the way up to 0. Okay, remember we don't equal 0 because 0 is the inflection point. Okay, that's when the second derivative was equal 0. Okay, awesome. So those are our things. Perfect. Okay, so find the intervals of concavity for all maximums and minimums, and points of inflection for this thing here. Okay, not a big deal. First things first, kind of like we always do, we figure out the first derivative. So f prime of x. Okay, so we should be getting pretty good at this by now. So 3x squared minus 24x plus 36. Okay, might as well figure out the zeros here, because that's the critical points, right? So take out the 3, we get x squared minus 8x plus 12. Okay, remember we want those points to equal 0. Okay, and then we factor this. So factors 12 add to 8, so that is 6 and 2, and they're both negative. Okay, so our x values here are 6 and 2. And remember, these are our critical values, so we could call them C if we really wanted to. Okay, all good. All right, so those are critical values. So those are going to be our maximums, minimums, maybe a point of inflection. It's possible. Okay, so anyways, let's do this. We're going to figure out the function at 6 and figure out the function at 2. So on your calculator, you just put in a 6 for all the x's up here. Okay, and when you do that, you get 4. When you put in 2, you get 36. So we have these points. We know that there's one at 6, 4, and we know there's another one at 2, 36. Now, we don't know if those are local maximums or minimums at this point. We just know that those are going to be the maximum or minimum points. Okay, not a big deal. Now we look at the second derivative. So I'm going to go right back up to this one before I factored, because it's just easier to take the derivative from there. So that is 6x minus 24. Okay, great. We also want the second derivative to equal 0. Okay, because that's going to give us any inflection point. So 6x minus 24. So 24 comes across, equals 6x. So x equals 4. Okay, so this is going to be an inflection point for us. Okay, so let's just go back over here. We'll go x is 4. Okay, or f of 4. Okay, so we figured that part out, and we put 4 into all of that, and we figure out that that equals 20. So that is the point 420. So this is a point of inflection. Okay, great. Awesome. So that's this guy, point of inflection. So I still need intervals of concavity and maximums, minimums. Now we know that 6, 4, and 236 are maximums or minimums. We just don't know which yet. So that's what the second derivative test is going to do for us. So we're going to make a little number line here. We're going to put 4 right in the middle, because that is going to define our regions of concavity. So we're going to do f double prime. Let's try 0. Okay, because that's down there. So f double prime of 0. So 6x minus 24, when x is 0, that's negative 24. Okay, so the important part is that's negative. So we have a negative region there. Remember, a negative region of concavity is concave up. Looks like that. Shoot, I got that wrong. Concave down, pardon me. Haha, funny. Okay, concave down. Okay, great. So this will be concave down. Now we're hoping the other side will be concave up, but we should still prove it. So let's just try 5 for this. So 6 times 5 is 30, minus 24 is positive 6, which of course is positive. So yeah, that's the concave up. Okay, great. So this part here is concave up. Nice. Now all we have to do is figure out where our potential maximums and minimums are in terms of this. Okay, so the first point, okay, it was at x is 6. So x is 6 is up in the concave up region. So if we're concave up in this part, or where that point is, so that means this guy has to be a minimum value. Okay, typically these are local minimums, but anyways, it didn't really ask that, just minimum, maximum, so that's a minimum. Okay, and then 236, see, that's in this region here. That's in the concave down portion, so this guy is a local maximum. Okay, so we have all our maximums and minimums. We have our intervals of concavity. Actually, I guess I didn't really write that, so we should. Okay, so f of x is concave down for negative infinity all the way up to 4, and f of x is concave up for 4 all the way up to positive infinity. Okay, and there's our 3 things. Awesome. Moving on. Yay. Now these ones start to get a little weird, because I'm trying to show you guys. Remember those notes where I told you that they almost always occur at f double prime is 0 and when f double prime is undefined, that kind of stuff. So these next few examples show some of that. So we're going to have fun. First things first. So f prime of x, So 3x squared minus 6x plus 4. Awesome. So let's see if we can factor this in the normal way. So 3, 1, 4, 1, 2, and 2. Okay. And the quick thing we notice is there's no factors that multiply and add to negative 6. It doesn't work that way. So, maybe my big X factoring doesn't quite work. So if you try decomposition or something, maybe it'll, we can check for sure by using the quadratic formula. So X, remember, this is negative B plus or minus square root of B squared minus 4AC all over 2A. Okay, so this will get us regardless of what method we use. Okay, so negative B, so B would be the negative 6, so negative 6 is just positive 6, plus or minus, so 6 squared is 36, minus 4 times A is 3, and C is 4. Okay, all divided by 2A, so 2 times 3. Wow, we did this a long time ago, everyone. Anyways, the important point here is, look what happens. This is negative 48. Oh, that's interesting, because if that's a negative, we can never take a square root of a negative, so that means f prime of x will never equal 0. It doesn't have any zeros. Okay, well, good thing we didn't waste too much time on it. So it will never equal 0, so that means there's no maximums or minimums for this thing. Okay, and that's weird because it's a cube, but it's okay, we'll just trust me. Okay, so it's never going to equal 0. So now we try the second derivative. Okay, so that's going to be 6x minus 6. Okay, well, we want that to equal 0 as well. So, hey, this is looking a little better. So then x equals 1. Okay, we can do it that way. I guess I could have brought the 6 over and divided. Either way, x is 1. Okay, great. So this point here, this is going to be an inflection point at x is 1. So I guess we should try that. Okay, so we'll figure out when is the function. So, okay, so f of 1. Okay, and what you do is you just grab your calculator out really quick. We can just do this in our head too. So 1 cubed is 1, minus, okay, 1 squared is 1, so 3 times 1 is 3, so 1 minus 3, okay, is negative 2, plus 4 times 1 is 4, so negative 2 plus 4 is plus 2, minus 5 is negative 3. Okay, so we have the point 1, negative 3 is an inflection point. Inflection point, or point of inflection, doesn't matter. Okay, so that's when the regions of concavity change. Okay, so again, we make a little number line here. Okay, so make a number line. Okay, so we put 1 on that. I'm going to do the dotted thing. And so these are going to separate our regions of concavity. So we go to f double prime. So 0 is over here, and 2 is a good one to check over there. So f double prime of 0 is, just negative 6. So that's negative. So that guy's negative. So that, again, is going to be the concave down. Okay, so concave down. And let's just make sure the other side is concave up. Sometimes it works that way. Most of the time it works that way. So we try 2. So f prime of 2. All right, so f prime of 2. 2 times 6 is 12. Minus 6 is positive 6. Hey, that is positive. So the regions, so f of x is concave down for negative infinity all the way up to 1. Okay, and f of x is concave up for 1 to positive infinity. Okay, great. And we've already decided there are no maximum and minimum values, so that's the only other thing we had to decide. So maximum, minimums, inflection points, and intervals of concavity. So these 3 are our answers. And of course, no max or min points. Now, if you want to graph that on your calculator, you can see that. What happens is this graph kind of looks like this, like that. So we've got an inflection point kind of down there, and as you can see, there are no maxes or mins. Crazy, huh? So concave up until 1, and then concave down until 1, and then concave up for this part. So, neat. Okay, moving on, a couple more. I know these are long, but I'm talking quite a bit, so all good. Okay, so this one here, ooh, it's a division one, so we might have a domain issue for this. Now, if you look at this, though, x squared plus 1, that's always going to be positive because x squared, anything squared is always positive, and then you plus another 1. So this guy here will never be 0. That's great, always positive. So we are never going to have a domain issue for this guy. So we check out the first derivative. Okay, so this is a quotient rule. So bottom times the derivative of the top. Well, that's 1 minus the top times the derivative of the bottom. Okay, so that's just 2x. Okay, all divided by the bottom squared. So x squared plus 1 squared. Okay, so we have a little bit of simplifying we need to do here. Not a big deal, just something we got to do. All right, so that's going to be x squared plus 1, right? That just distributes, and then those distribute as well. So then we're going to get negative 2x squared all over x squared plus 1 squared. Okay, and we want this to equal 0, so we might as well put those zeros in. Okay, so that's going to be negative x squared, right? X squared minus 2x squared is negative x squared plus 1, all divided by x squared plus 1 squared. Okay, so there's our first derivative. Not a big deal. Okay, remember that little trick? The zeros always come from the top part, right? If I multiply that bottom part up, it just equals 0. So to find the critical values, we're going to go negative x squared plus 1. Okay, so the negative x squared just comes across, so x squared equals 1. So x equals plus or minus 1. Okay, so that's nice. Those are our critical values, so we can say equals C. So those are going to be our potential maximums or minimums. So because we want points for this question, we're going to figure out f of negative 1 and f of positive 1, because those are going to be our maximum or minimum points. So we just put in negative 1 into that equation, and you end up with negative 1/2 when you do that. Okay, positive 1, 1 over 1 squared plus 1. 1 squared is 1. 1 plus 1 is 2. So that's just positive 1/2. So we have these points here. Now I'm going to erase this little guy because I kind of... Okay, good. Okay, so our point here is negative 1 and negative 1/2. And positive 1 and positive 1/2. Now those are going to be our potential maximums and minimums. We just don't know which yet. So we're going to find that out though. Next up, we figure out the second derivative. Okay, now this is going to need a little bit more room here. So I'm going to just, you have more room on your page, but f double prime of x equals. So we go right to the simplified version. Okay, and I wrote it right beside, it's right there. Okay, so again, it is the bottom, so x squared plus 1 squared, bottom derivative of the top, so that's negative 2x, minus the top, which is just negative x squared plus 1, times the derivative of the bottom. Well, that's a little trickier, but that's okay. So you get 2x squared plus 1 to the 1, okay, and then we chain rule, and that comes out as a 2x. Okay, all divided by the bottom squared again. So x squared plus 1 squared, and squared again makes it to the 4th. Okay, so this is where we do some of that crazy factoring that we did. Now let's just rewrite it one more time, just kind of doing all the distributive stuff. So negative 2x comes in front. X squared plus 1 squared. Okay, now this 2x and the 2 are going to come in front. Okay, so that's going to be good. 2x and the 2, okay, comes in front and makes a minus 4x. Okay, and then we have the negative x squared plus 1, and then we have an x squared plus 1. Okay, all divided by x squared plus 1 to the 4th. Okay, so now we're going to just factor. So if you have a look at this, in each term, now I'll write in blue for a second here. So there's the divide line right here. So those are where the two terms are. So for each term has a 2x. So I can factor out a 2x. You know what? I can even factor out the negative 2x. That's kind of handy. So if I factor out negative 2x, now look what else they have. Each side, that's got an x squared plus 1 squared. This has an x squared plus 1. So each one has an x squared plus 1 that I can factor out as well. Okay, remember we put square brackets around for those. Okay, so we factored out the whole 2x, and we factored out one of the x squared plus 1s. Okay, so that's still there. Now we have the minus 4x. We factored out a negative 2x, so what's left is a plus 2. Okay, we took the x out. We still have this negative x squared plus 1. That's still there, but we factored out the x squared plus 1. That's all gone, so that's this part. And still dividing by x squared plus 1 to the 4th. Now, if you have a quick look before we even simplify those square brackets, we have an x squared plus 1 to the 4th and an x squared plus 1 on top. So one of those are going to cancel, and we're going to end up with an x squared plus 1 cubed on the bottom. All right, so now let's go back to those square brackets. Okay, so we have, this is going to distribute, so that's, I'm just going to write over here for a sec, so that's going to be x squared plus 1 minus 2x squared plus 2. Oh, wow. Okay, that's no big deal. It's all good. So x squared minus 2x squared is negative x squared, and 1 plus 2 is plus 3. Wow, that is huge. So that is our second derivative. So f double prime of x. Now remember, we want that to equal 0 in the end so we can find our inflection points and our regions of concavity. Whew. Okay, so we make that equal 0. Remember, that guy multiplies up. He is just 0. So the zeros just come from the top. Okay, so right over here. So 0 equals negative 2x, negative x squared plus 3. Okay, so that looks good. So this guy here, having an x all by itself, that means x equals 0. Then we have this term. Okay, well, that has to equal 0 as well. So then we got negative x squared plus 3 equals 0. So the negative x squared can come across. So 3 equals x squared. So square root, so x would equal to plus or minus root 3. Now we're going to leave it as a root 3, but I'm going to put the decimal here just so we can kind of see it. That's plus or minus 1.73. Okay, so those are our three zeros. X is 0, plus or minus 1.73. Okay, great. Wow, I'm really running out of room here. That's okay. It's not a big deal. I will figure it out. All right, so we have put our regions of concavity down here then. Okay, so we have negative 1.73 or negative root 3. 1.7, it's supposed to be a 7, everyone. Oh, now I'm just making it worse. Alright, so negative 1.73, we have a 0, and we have a positive 1.73. Okay, no big deal. So those are our regions, and we want to figure out numbers on either side of those. So negative 1 is in here somewhere. Negative 2 is out here somewhere. Okay, positive 1 is in here, and then positive 2 is out there somewhere. So we're going to check for our different regions. So we're going to check f double prime of negative 2, f double prime of negative 1, f double prime of positive 1, and f double prime of positive 2. Now remember, all we're doing is checking for the negatives. Okay, so 0 is the other one, and 1.73. So those are our regions. Okay, so when we try f double prime of negative 2, we end up with a negative number. And all we do is we just type that into our derivative. Okay, when you type in negative 1, you get a positive number. When you type in positive 1, you get a negative. And when you type in positive 2, you get a positive. So I should probably write in red again so you can see kind of where I'm going. Okay, so this region, that was negative. This region in here is positive. This region in here is negative. That region in there is positive. Okay, so those are our regions of concavity. Okay, whew. Wow, this is crazy. All right, so here, I'll write up here for now. Okay, so f of x is concave down. Okay, those are the negative ones. Okay, so the concave downs are from negative infinity all the way up to the negative 1.73, which was the negative root 3. Okay, unioned, yeah, see, not enough space. Unioned with the other negative one, so that was from 0 to positive 1.73, which was 0 to positive root 3. Okay, so that's our first region of concavity. Our second, so f of x is concave up for the positive region, so that's the negative root 3 to 0. And then from the positive root 3 all the way up to infinity. So those are our regions of concavity. Wow, I know it's hard to follow. I'm so sorry, guys. Okay, so that's the regions of concavity. Now, the inflection points, that's when it equaled 0. Have we done that yet? Yep, second derivative equaled 0 at those points, so we have inflection points. No, we have the x values for the inflection points, so points of inflection. Okay, and so we know that our x values, we'll figure out the y's here in just a sec. So the x values was negative root 3, 0, and positive root 3. Okay, so we'll have to figure out the y values for those. Okay, now before we do that, we might as well figure out the max and mins. So look, our first guy here, we know that those are potential maximums and minimums. So negative 1 falls in this region. That is a positive second derivative, so that is concave up. So if this is concave up, so it's looking like this, so this guy is a minimum. The positive 1/2, that was in this region here. Okay, so that is a negative, so that is concave down. That's that, so this one is a maximum. So those are our maximum and minimum points. Okay, and then we've got to find some more room here. All right, so the original function at f of root 3, okay, f of 0 and f of positive root 3. Okay, we need to figure out those because we need the y coordinates for our points of inflection. Okay, so when you type that in, you can get crazy decimals, so negative 0.43. That's just negative root 3 over 4. Okay, so negative root 3 gives us a negative root 3 over 4. So that's the inflection point. When we type in 0 into our function, that just worked out to 0. Okay, so 0, 0 is a point of inflection, and then positive root 3 gave us root 3 over 4. So that is our other point of inflection. Okay, and just for the fun of it, that is negative 0.43 and positive 0.43. Just if you want to graph and kind of have a look. I know that's really jumbled. I'm so sorry, guys, but it's the way it is. It'll be all right. Okay, you can go through that again and spread it out if you want. Just all good. Okay, and then the last couple here. I know you're thinking this is so long. I'm so sorry. Okay, these ones are the kind of weirdo ones. So that last one was kind of long, but D shows some of those interesting things that I was talking to you about with the notes. Okay, so first things first, we take the first derivative of this. So that's going to be 1/3 x2. Okay, so 1/3 minus 1 is negative 2/3, and then the 2, of course, just doesn't do anything. So this guy here is, so 1/3, so that's going to be 1 over 3. Then we have a root on the bottom, so this is going to be a cube root of x squared. Okay, so that is the first derivative. Now, even though there's not a domain issue for the original function, there is a domain issue for this guy. We know that x cannot be 0, at least for the first derivative. Okay, because if x was 0, we would be dividing by 0, and that just wouldn't work. Okay, now, the crazy part about that is, if you look at this, there's no x's on the top, which means if the bottom can't equal 0, which it never can because you can never divide by 0, then, and the zeros always come from the top, so 0 equals 1, okay, because remember that bottom part comes up, multiplies by 0, doesn't work, so 0 equals 1. This is impossible. 0 can't equal 1. So that means that the first derivative will never equal 0. F prime of x will never equal 0, so there's no max or min points for this graph. Okay, well, fair enough. Yay, no maximums or minimums. So now we try f double prime of this thing. Okay, so we're going to go back up to the first shot at it. Okay, so then the 2/3 comes down, so that's going to be negative 2/9, right? That 2/3 comes down, and then x2, okay, 2/3 minus 1, that's negative 5/3. Okay, so the negative 5/3, of course, that flips to the bottom, so that's going to be negative 2 over 9, cube root of x to the 5th. Whew, that's crazy too. Now, but the thing is, this guy still, x cannot equal 0, right? Because then we would be dividing by 0. And when we set the second derivative equal to 0, we have the same problem as before. So the 9 cube root of x to the 5th multiplies up, so 0 equals negative 2. So that doesn't happen either. So that means f double prime, okay, will not equal 0. Will not equal 0. Okay, well, remember what our notes said, though. The points of inflection happen most of the time when f double prime equals 0. Well, this doesn't happen. And sometimes when x double prime is undefined. So f double prime is undefined here. So this guy is a possible point of inflection. Okay, so we have to test him. Okay, so f double prime of 0. Okay, that is a possible point of inflection. Okay, great. Oops. Okay, so we're going to test that guy. Now, right at 0, so we're testing regions of concavity. So remember, it's a point of inflection if the regions change. So negative 1 is out here, positive 1 is over there. So let's check negative 1 in the second derivative. Okay, so let's see, negative 1 to the fifth is negative 1. Okay, and negative 1, the cube root of negative 1 is negative 1. 9 times negative 1 is negative 9, and negative 2 divided by negative 9 is a positive value. Okay, positive 2/9. Okay, well, all right. Fair enough, so that's positive, and then we try positive 1 there, so that's just going to be, that's all going to be positive 1. 9 times positive 1 is just positive 9. Negative 2 over positive 9 is negative 2/9. So hey, look, that does change concavity, which means that the point 0 is a point of inflection. So, all right, even though f double prime didn't work out, there was no zeros for it, it was undefined at x is 0, but our original function isn't, right? F of 0 for the original function, so x to the 1/3, so 0 to the 1/3 is 0, okay, and then plus 2, so f of 0 is just plus 2, okay, so that means that 0, 2 is an inflection point. Okay, and there are regions of concavity, so f of x is, okay, so positive is concave up, for, let's see, that is negative infinity up to 0, and f of x is concave down then for 0 up to positive infinity. Okay, remember we've already decided that there are no maximum or minimum points, so that is all we've got. I know that's a weird one, but that's okay. If you have a look at the graph for this, it's kind of funny. It does something like this, and then like that. Okay, so there's the inflection point at 0, 2, and there's no maximums, no minimums. It just goes out, and it looks very strange, but it's one of those weird ones. Okay, all good. And then the very last one, and then I promise I'll stop talking for a little bit. Sorry, guys. So this is x to the 4th. Okay, at first glance, it looks like it should be easy. So f prime of x is 4x cubed. Okay, well this happens when, it's 0 when x is 0. So then f double prime, okay, so we're going to have a maximum or minimum at x is 0, so if we go f of 0, okay, well that's 0 to the 4th, which is 0. So we know we have a potential maximum or minimum at 0, 0. Now, you guys know what x to the 4th looks like already, okay? It looks like this, right? A really pinched parabola, okay? X to the 4th, so it should be 0, 0 there, okay? So that should be a minimum, but we're going to prove it, right? So f double prime of x, so that is 12x squared, okay? Well, that also equals 0. Okay, so f double prime 12x squared, so x equals 0. So, now, here's the thing. This point should be, f double prime is 0, should be a point of inflection. But there's something weird here. So let's just follow this through. Okay, so do our regions of concavity. Okay, awesome. So that's 0. So let's try a point -1 and +1. So let's see. 12x squared, so if x is -1, -1 squared is 1, times 12 is 12. So f double prime of -1 is positive 12. Okay, so this is positive. So the other side should be negative. But f double prime of +1, wait a second, 1 squared is 1 times 12 is still 12, which is still positive. Wait. So it the regions of concavity didn't change, which means that is not a point of inflection, even though f double prime was 0. So it's very interesting how that worked out, but this 0, 0 is not a point of inflection. So 0, 0 is not a point of inflection. Not for this particular graph anyways, okay, because they're both concave up. Wow. Okay, awesome. So now, the question, we wanted to know whether there were maximums or minimums. So 0, 0, well, what is that? Okay, we have it's concave up on this side, and it's still concave up on that side. Okay, now because they're both concave up, we're obviously approaching a minimum. Okay, so this is a minimum. Okay, good. So 0, 0 is a minimum. The regions of concavity, it's concave up the whole time. Okay, so concave up the whole time. Well, technically the whole time. Not at 0, right, is concave up for, for negative infinity to 0 and from 0 to positive infinity. We can't just say as an element of the reals here, because at 0, it's neither. It's not concave up or concave down. It's undefined, right? At least the second derivative is. So we still have to have the region separated like that. But, so those are the regions. It's a minimum, and there are no points of inflection for this graph. Wow, I know that was really long, guys. I promise the next one will be shorter. Call me if you have any questions. Thanks.